Shall we get started? Yeah, while people wander in, I'll start things off. So I'm going to keep this on the whiteboard to remember our goal. So, basically, as I explained in lecture yesterday, no matter what anyone says, I don't see any motivation for Q learning, except for it always works. In the tabular setting, you're computing this Q function, which gives you the optimal policy. Outside of that, we're solving what's called the projected Bellman equation, which sounds beautiful, but so what? So I'll review that in a moment. There's no motivation that I know of, except it always works. And so that's a huge scientific question. It's how to understand why Q learning works in practice. But I have no answer for you. It's just. But so the obvious thing to do instead is, there's a typo here. Is to look at a parameterized family of policies and try to find the best policy in a given class. Because after all, we had a family of Q function approximations, and they were derived just to get a bunch of policies. Why go through that circuitous route? You could just start with the policies. Somebody gives me a family of randomized policies, and I want to find the best in the class. And so if you were at Deb's talk, you'd see that this fixed policy Q function played a crucial role. And so we're going to talk about that. So the first half of the lecture will just be about understanding this. And there's a sort of a fallacy. You have to estimate this. You don't, which I'll explain in today's lecture. And that was the main contribution of Conda's thesis around 2000 at MIT. So two things, got to understand this. And then the actor-critic method, the way to do gradient descent based on this I think it's pretty straightforward. I don't know if it's that technical. We'll see. See what you think. Now, why randomized policies? It's because, if you've got a discrete state space, I'm not going to expect a differentiation if I'm looking at deterministic policies, because there's only a finite number of policies. So you need smoothness. You need a smooth family of policies. It's really unfortunate because you can imagine if you're trying to do gradient descent, and you've got a really rich family here, well, the optimal policy is deterministic, So basically, that theta is going to have to go to infinity. When you apply the gradient descent methods we're going to talk about, you're going to have a regularizer. Because if you've got a really good policy in your class, it's likely deterministic. The only way to achieve that, for the kind of things we're looking at, is for the norm of theta to shoot off to infinity. Anyway, that's just one preview. All right, so part 3. So again, I've got to do both. I've got to do TD-learning and then talk about, because that gives me my critic in the actor-critic method. All right, yeah, so quickly, there's some resources. Although this is tricky for me, as I mentioned. You can go and look at chapter on 10 of the book. And here's the thing that Paul Schweitzer in 1969, introduced the sensitivity theory for Markov chains. And I can mention a half a dozen researchers who claim they invented it in the 80s and 90s, but Schweitzer did in the 60s. And there was work by Peter Glynn then on gradient descent, for things like this, not in MDPs, but more generally, and work by Borkar and others. And for me, I learned all this stuff from maybe 2 theses, Ben Venturi and Vijay Kanda. And I know from reading their work that Sutton and Barth are incredibly inspirational, as well as Williams, which led to reinforce. And there could be a mistake there. I just didn't even bother to correct it because I had a lot of trouble understanding some of those old papers, partly because of all the psychology language it's thrown in and stuff. There's so much discussion that I don't understand. And then there are equations, and and a lot of it I just can't parse myself. So after seeing Deb's talk, I felt a bit embarrassed because he was talking about how Williams did have a lot of the ideas here. And I had meant to go back and look over it, and I just forgot. So homework is, we don't have a tutorial session this afternoon, I mean, for this talk. Our tutorial is to go and see what Williams actually did in 1992. I've got a copy of the paper if you want it. But definitely missing is the incredible elegance that you don't have to estimate this monster. You don't have to at all. And that was Condit's contribution in 2000. Oh, I actually guess maybe early in 1999, 1998. And they're given no credit whatsoever. If you look at the papers on PPO and all that stuff, there's no mention of the Condit's beautiful thesis. It just blows my mind. So I deeply respect the work of Richard Sutton and his colleagues. It's just the technical aspects haven't been as valuable to me as the stuff at MIT. Is that? So I respect you, Rich. Seriously, I mean, I just have to be careful because I think there might have been a territorial battle back in 2000. It's possible. If you look at the literature, it's interesting. Okay, so this is a joke, but it's just, I love this little stupid joke because it's about oblivious training. If I'm going to go and try to train, for some optimization procedure, and I'm a mouse that wants to find cheese, after glancing at the cat, it will never go there again. Yet if you do this sort of oblivious training for TD-learning or Q-learning or any of these algorithms, the algorithm will go, oh, there's a cat. Ooh, oh, there's a cat. Ooh, over and over an infinite number of times. And so that's the motivation for exploration. You basically slowly realize, yeah, there really is a cat there, and you stop visiting there. And you more and more often, and you poop as well, you avoid that, and quickly go there. But this is just like examples where it takes a million iterations and you still haven't converged. If you do some oblivious training in Q-learning, it's exactly like these examples, like Bart's example, or lots of others. So yeah, so keep that in mind. All right, so I'm just basically going to repeat what I said yesterday. I've got an MDP, and I don't really need this talk about sets because we're going to be looking at finite state space and finite action space. But the probability of going to some set, given the previous state and action or input and all the prior history, only depends on the current input and the current state. That's called a transition kernel if it's a general state space. And I'm going to, for simplicity, I'm going to only look at discounted cost. And the thing we looked at for Q-learning was Q star, which was the minimum overall policies of this guy. Okay, but today I want to look at fixed policy Q functions where I don't take a minimum. I have a given policy, and I have that for reasons which won't be clear, later on. And then there's this Bellman equation. And once again, okay, so Watkins came up with this in this tabular setting. And again, there are two reasons why this Q function is so beautiful. One is that once I have it, the minimizer over U is the optimal policy. So it's the thing we really would like to have. And number two, you get a minimum within the expectation. And that's what enables Monte Carlo methods. If we only looked at the value function, the minimum would be outside the expectation and we'd be screwed. We wouldn't be able to use all these cool Monte Carlo methods. Stochastic approximation, it doesn't work when there's minimum outside. All right, we don't have the root finding problem we want. No, because, and again, I could see somebody getting really mad at me about this, but if you look at the original source of paper, why is it never got published? It never got published. It was some sort of preprint, I've forgotten, and it never made it to a journal. I'm sure a reviewer pointed out, hey, all you're doing is you're calling XK UK the state and applying TD-learning. Now the thing is, the reasons I could imagine if this was an RL conference, everybody be yelling at me is because everyone has reinterpreted SARSA in their own way. So some people interpret SARSA as something like a softened Q-learning, where they're constantly changing the policy. But if you look at the original paper, SARSA and TD-learning are identical. Sarsa is magic for the same reasons here, because you're estimating, well, you estimate, I mean, yeah, Sarsa aims to estimate this. And it's magical because it enables unbiased off-policy TD learning. And if you don't try, if you're not looking at the state action value function, it's harder to do off policy. And there are cases when you really want to train without the policy of interest. For example, in deterministic optimal control, it may be your goal is to go to the origin and stay there forever. And so the steady state distribution is a point mass of the origin, and it destroys the theory completely. So you need to add some noise. Yes, there's a long essay in my book about why I just avoid the term Sarsa completely in the book. And I'm just waiting for somebody to yell at me about that, because I mean, yeah, the language isn't settled. Yeah, so I mean, yeah. But okay, so slightly different notation there from there. But I mean, if I'm given a fixed fee, here I've got a deterministic policy, but could be stochastic. So that, again, that's the fixed policy Q function. Its initial motivation was for policy improvement. So if you compute this exactly and you construct a new policy based on the argmin, it's strictly better. So basically, the performance of this policy compared to the original policy is better in the sense that the discounted cost is smaller for every x in u, or less than or equal to for every x in u. So you get this monotone behavior. But the reason I'm obsessing about it today is the sensitivity formula that actually Deb wrote down on Tuesday, and I'm going to explain in greater detail. Now, for the average cost problem, we require gamma equals 1. And this is the solution, what's called Poisson's equation. So you notice I got rid of the gamma, but I normalized it. The tilde means that I'm subtracting off the mean. Whenever you see tilde, it means I'm normalizing so it has 0 mean. But it turns out that's equivalent. See, this is not very useful because you're summing to infinity. And so if you tried to use this in an algorithm, you'd have infinite sums. It turns out that's equivalent to a sum up to some target state just before. So that tau bullet is just the time at which xk, uk reach some target, any target that you hit infinitely often. And I don't care about constants, so you can use this. This leads to nice algorithms because it's a random sum, but it's finite. Right? Now, I'm not going to get into this much because nobody does this. In practice, everyone ignores the theory completely, and I expect you will too. So I'm going to really skip this completely. I'm just going to talk about the discounted case. All right, we just don't have time. But I just want to mention that we have that. Oh yeah, by the way, so yeah. So I should say there's a DP equation. Yeah, so yeah. The last time I talked about gamma equals 1, okay? This, forget you ever saw it. But so this deep, this fixed policy Q function satisfies the same sort of dynamic programming equation, but I'm still using this min notation, but now it's evaluation rather than min. The notation is completely consistent because what I'm saying is I'm making my action space a singleton for each x. For each x, I'm minimizing over a singleton, which is phi of x. So it's nice to be able to keep the same notation in both cases. So as a fixed point equation in Q, what's valuable is this is now linear. It's a linear in Q as a function. And that's why TD learning is really easy compared to Q learning. When if this is actually a minimum, then I've got this concave function shoved in here, and it's what the hell is that? A fixed point equation with a concave right-hand side isn't something comfortable to work with. But when it's just evaluation, that's a linear operation. This becomes a linear equation. And that's why Ben Van Roy was able to build this amazing theory. And that's where the first half of this is. It's all of Ben Van Roy's thesis in what is it, 96 or something? I don't know. Yeah. All right. And then you've got the same sort of Galerkin relaxation that is looked at. So, Sutton, he wasn't, even though he used the language of stochastic approximation, he wasn't an expert at the time, but he understood that basically I'd like to set this equal to 0, just like before. I choose some d-dimensional eligibility vector. And if this eligibility vector doesn't depend on theta, and I've got a linear function class, this is just a linear equation in theta, so you can just solve it in one hop, as I will show. All right. Okay. All right. So I'm going to stick to a linear family for reasons that will become very evident, because unlike before, like I showed you the mountain car example, where you have this horrible value function, it's discontinuous and all that. I don't want to estimate Q theta. I don't need it. You can get away with murder, and it's without loss of generality you choose a linear function class, because we don't need a real approximation of Q theta. It's completely wild. And I'm teaching you the theory, and nobody ever uses it, and there might be a good reason, but nobody's ever explained why. So in practice, people always try to estimate the Q function. I think that's a fallacy. I think. All right, so I'm just gonna try to explain this to you in the next, just over an hour. Okay, so again, if it's a linear function class, that's a linear function of theta, that's a linear function of theta, and that, with our conventions, is just going to be psi, evaluate the current state in action. And so you can just do a simple matrix inversion, you've got the solution, you're done. All right. For a neural network, yeah. But you basically, with a neural network, you'd stick in grad of Q theta there. There's no real theory unless you zap the zap algorithm. But there's zap. But we don't need to, okay? We don't need to. Now, the choice of eligibility vector that you'll find in the literature is TD lambda. And you take the gradient of the Q function, which was our first choice for an eligibility vector, but you pass it through a low-pass filter. So this is a low-pass filter with a first-order low-pass filter. And you're taking the discount factor times this lambda value, which is between 0 and 1 again, and that's it. Now, so before I told you, take lambda equals 0, it's what everybody does. But for the theory, we have to take lambda equals 1, and then the theory is beautiful. But there's the algorithm. I mean, remember, goal. Still the same goal, f bar of theta star equals 0. F bar of theta star. So we basically have to take that on the right-hand side of our stochastic approximation algorithm. So there's the recursion. We've got exactly the thing that appeared on the right-hand side before times this eligibility vector, and this infinite sum can be, just expressed recursively like that. We've got this contraction term here, gamma lambda, and then this term here, which for me will always be just psi n. This is going to be, because I'm going to look at linear function classes. So it looks just like Q-learning, just the definition of the eligibility vector. I mean, the Bellman, the temporal difference is changed because I've changed the meaning of the underbar. Now it's evaluation rather than it's evaluation rather than minimization. Now, going back to this point about SARSA, and something I didn't say loudly enough last lecture is that when you go through all this, I could take I mean, this previous equation, this I can say this is true for any input sequence. Not the input sequence I care about. I could just take some IID input, and this would still be true. And that's the beauty of the Sarsa formulation. The fact that you can. When I'm writing this down in terms of a Q function, this is valid even if U is not not the right input. If it has nothing to do with the input that I am interested in. But there I've got this evaluation here, which makes it work. So as long as it's the stochastic approximation is stable, it's going to solve the problem, this molecular relaxation, and maybe give you something meaningful. Now, in the on-policy case, again, I'm sticking to deterministic policies just for ease of notation. You could always extend the state space, include some IID noise that models the randomness. So it's without loss of generality. In on-policy, what happens is that if I look at that Q underbar, by definition, that's Q theta. Well, there's no theta there. Yes, there is, just xn plus 1. All right, so this underbar just meant substitution in this case. Well, I can just say that's un plus 1. Okay, and that's a setting that was analyzed in Ben Venore's thesis and all, and where everything's very, very elegant. And we'll stick to that. Basically, in the implementation I'm talking about, we'll stick to the on policy training, if you like, and we can get away with it because in this theory we're choosing. We aren't choosing deterministic policies. We're choosing randomized policies, and they're designed so we really do a lot of exploration. So it's not a problem. But then things really, really simplify. I mean, this function, you've got a Q theta xk uk, then you've got a Q theta xk plus 1 uk plus 1. It really falls apart into something very, very simple, as I'll explain. All right. All right, so I don't want to talk about ZAP yet. In fact, I even want to skip that. To hell with it. I forgot that I don't need this detail. We might as well look at the linearization, but I want to, I do need this, but for a linear function class, that this linearization matrix here, when I take its mean, I would get A. This doesn't depend on theta at all. So let's stare at this. I'm looking at the on policy case where I don't have to do this evaluation. It's just un plus 1. That's my Q one step in the future. That's my Q estimate right now. That's my cost function. So you can do the pattern recognition and see that this B is just a expectation of this product. And you see I get a psi transpose. That's like a autocorrelation matrix. And I get a psi n times psi n plus 1 transpose. That's a one-step lag autocorrelation matrix. So I could write this down as equal to here I've got a minus R0 plus gamma R1 theta plus the expectation of, psi n times Cn. There you have it. All right, so pattern recognition, psi n plus 1, that's R1. It's basically that. So even if gamma were 1, it turns out if the covariance is full rank, covariance, not the autocorrelation, this matrix is Hurwitz, you can show. And with the gamma there, it's really easy to see it's Hurwitz. So the the eigenvalues are in the left half plane. And in particular implies it's invertible. So when I set this equal to 0, I just get theta star is A inverse B, and the inverse does exist. And that's it. All right, so there's not much to it in the on-policy case. Now, off-policy, that's no longer true. So, what happens is if you can't just substitute in here, then you no longer have an interpretation like this. And that's when you can get instability. That's why Bard's example comes up. But you've got robustness when you have stability. So as long as if you did it off policy, as long as it was a epsilon perturbation of the on-policy policy, you're still going to have a Hurwitz matrix, and it's going to work fine. And that it's not going to be relevant here, but it's nice in other other settings to know that. Is that clear? I mean, it's really, this matrix theory is really needed. All right, but I just want to skip all this crap. I don't care. I don't care. All right, I want to do this. Forget this. We need the Blackboard. So it turns out what we need is LSTD is ZAP. Forget all that. This is least squares temporal difference learning is essentially estimate A, estimate B, and divide. It's a recursive form of that, but that's all it is. All right. And it's just a tweak on ZAP. What can I kill? Oh, that's right. These things swing up, don't they? Do they? Oh, how sweet. You don't realize you live in paradise. I mean, this is J.D. Vance is wrong. You guys won. Now forget all this crap. Suppose my goal, new goal, all right. So you notice I introduced some notation here. I just don't want to have to keep on writing XK, UK, so I'm calling that CK. And that's about my point about TD-learning and SARSA being the same thing. Is that TD-learning, in SARSA, you're estimating a fixed value function for phi rather than x. I'm not saying it's incredibly valuable. It's insanely valuable, but in terms of the initial contribution, it was just a difference in notation. But in terms of its impact on theory, it's insanely important. I just know I need to do this in the Blackboard. So I've got a linear function class, and I forgot the theta. And I put a phi there just to make sure it's really different. And I've got a linear function class. So if I wanted to minimize this, I take the gradient set equal to 0. And I'll put a half there. So because when I take the derivative, I'm going to go and have to deal with that 2 I'm going to get rid of. So I take a gradient. What do I get? So I'll take the gradient of this. I could take the gradient inside. This is a linear function of theta. It's sort of silly. It's a quadratic function of theta. So it's kind of silly to talk about calculus. We could just solve a quadratic equation, but let's pretend that's not the case. So if I take the derivative, I'll get this times the derivative of the inside. All right. So I get the error, and that phi is annoying. Let's just get rid of it. I only have a q over there. So that's the true q function. It's q theta over there. And I've got this error. Now, this is just psi. Psi k just means psi evaluated at phi k. And this is just psi k transpose theta. Right. That's a scalar. That's a vector. I can move these things around. And I'm going to get a psi k transpose times theta. That's what I called R0. And then minus this thing. So we have a solution. And it looks a little bit like TD lambda learning. Theta star is R0 inverse times this nice vector. All right. Oh, the R inverse missing. Oh, no, there isn't. I'm sorry. All right. I've got, this is 0. So I've got the dependency on theta is this linear. I've got R0 theta. And then I've got the basis vector times q right there. And that's annoying because it's something I don't know. So the estimating this R0 up there, estimating that autocorrelation, just go through, just like in TD-learning, you can just go and take sample path averages. But that looks like it would stop you cold, But let's play around. And I'm going to replace that with a 0. All right, so C of Q phi K, I just replace K by 0. This is all in steady state. I can shift time any way I want. And we know that Q is a conditional expectation, right? This infinite sum here. If I multiply this by any function of x and u, it can come inside. That's all I'm doing. So I can happily. There's an expectation outside. The fact that this is a conditional expectation doesn't bother me. And now what I can do is I can play with time again. And for each n, I can subtract n here and subtract n there. So what I'm doing is I'm looking at this phi n process on the two-sided time interval. So it's a stationary process where time goes from minus infinity to infinity. So I'm free to go backwards in time. And the real motivation for that is that I don't want about something in the future. I want things in the past that I've seen. So when you do that, look what happens, everybody. Well, keep the expectation. Well, no. So I'm going to subtract n there. I'm going to keep my n there. Minus n gamma to the n. Does that look familiar yet? Well, remember the low-pass filter business. If I take the sum back inside and take the gamma back inside, I get my eligibility vector. I'll just write it down and then explain. This is equal to the expectation of C of phi 0, eligibility vector 0, which is equal to the expectation of C of phi, I don't know, n, eligibility vector n, where the eligibility vector is over there. Let's go back and look at that. I don't want to write that down again. Eligibility vector, where are you? Right there. See? If I set lambda equal to 1, and I remember the gradient of q theta is just psi k, you know? That's what that is. I'm summing from n equals 0 to infinity of gamma to the n, psi minus n, right? That's the eligibility vector at time 0. Right? So that was discovered in Ben Van Oor's thesis, you know, and you know, just mind-boggling at the time. It was really exciting that you're solving this minimum norm problem when you do 2D1. That's it. I don't know how he came about it. I don't know if he was just playing with the equations that had popped out, or if he just initially said, "Huh, what if we can do this?" Now, the thing is that there's no motivation at this point for this. Why would you want to minimize the L2 norm? It really doesn't imply anything about performance or anything like that. But then it turns out, so Ben Van Oor did all this for mathematical fun. Then comes along Conda, and it's like, what the hell? This is what I need. This turns out to be the fact that the TD1 solves a min norm problem just cracks actor-critic methods. It just makes it incredibly practical. All right, so that's what I'm going to explain next. Questions? I know that half of you are lost, and we haven't covered that much, so it's easy to catch up. Let's just go through this again. I mean, I don't know. I mean, you know, I've got a quadratic form here, you know, and when I take the derivative, I get the error times the derivative of that. Everything's linear, so that's why I get a basis vector. And this fun thing about using stationarity here. That's it. This is subtracted n. You know, because I don't like having to have something like I was using stochastic approximation. I don't want something that depends on future states and inputs. And so by using stationarity, I move things backwards in time and I look at past regression vectors, you know, making everything causal. You know? And so I get this wonderful formula. And so you can just go through and estimate R0 by Monte Carlo and estimate, you know, this product, this expectation to Monte Carlo, divide and you're done. You know, or you can do it recursively, you know. You can use this you know, TD1 algorithm and have it go. Now, why do you think nobody ever does this, by the way? You know, I mean, you will never see anybody do this. What? Oh, no, right there. So there's R naught. It's the autocorrelation matrix. It's the thing that came up here because I had an expectation of psi and psi and transpose, and I called it R naught. Oh, no, but right here. So I've got an R1 there. That's the expectation of psi n times psi n plus 1 transpose. Oh, no, just I have a linear function class. Yeah, so I'm assuming throughout, and I'll see that's justified. that I don't ever have to look at anything but a linear function class. Using actor-critic methods with a neural network for the Q functions is a mistake. As far as I know, it doesn't make any sense. A linear function class is what you want. And I guess, I mean, someday I might be proven wrong, okay? But the theory says you shouldn't do that. You should use a linear function class, and I'm going to show you a really simple one, just a baby linear function class. Okay, so I will tell you which linear function class in just a moment. I'll be very explicit. All right. So yeah, forget all this stuff. Yeah. All right. And so, so this is what we just said. So basically, I just explained how when you minimize this, you get TD1. And what we're going to see next is that this leads to a way of performing stochastic gradient descent without bias, with a really, really stupid approximation of the Q function that's not even an approximation, it's crap, but it gives you an unbiased estimator for the gradient. So that's the second half of this lecture, which I'm starting now. People are awake, that's good. All right, so remember this. And the thing to really keep in mind, everybody wake up right there, doing this, solving this minimum, norm problem, I get the error is orthogonal to the regression vector. That's really everything. Okay, I can just go home now. I don't need, what we're about to find out is that I don't care about, when we get to these actor-critic methods, I don't, like Deb shoved in a Q function, I don't need it, because what's going to happen is I'm going to only need to know the expectation of Q times the regression vector. But that's the same as a stupid estimate times that. And that's the thing. So this formula is what's critical in making the actor-critic method work without bias. The fact the expectation of the real Q function times psi is the same as my estimate times psi at theta equals theta star, not 0 star. There's no 0 star in this lecture. Okay. So I don't know, Kaya was saying this lecture is too technical, very technical. I don't know if it is. I mean, there's one technical result there, it's minimizing a quadratic form, and there's a little bit about stationarity there, but that's it, and the fact that stochastic approximation works, that's technical. The fact that you can solve this problem with this algorithm. Yeah, I mean, this is least squares temporal difference learning. And the fact here that A hat, A is now just R0 minus R0. So it's this estimation here is just estimating that autocorrelation matrix in the R0. All right. Okay. I forget this. Forget this. So there's a whole bunch of stuff on how to make these things work better. I just don't think we have time. But if you go back to if you go look at my networks book, you can see total failures. And one solution was to introduce state weighting in the objective, all that, forget it. We don't need that here. Everything relative, blah, blah. Yeah, by the way, relative LSTD is magic for TD learning. The theory is complete. It's not like in optimal control yesterday. There, it's just elegant, so, but forget that. Let's go to the actor-critic method. Now, here's where I get nervous, okay? So, I've got a notes section in chapter 10. I was in so much pain writing this. I spent months going over it, trying to go into the literature, and I still don't think it's correct. But it basically goes through Glynn's work in the 80s, and there was work by Borkar back then as well. And I mentioned, Seidman before in the 60s. And there's like almost no mention of Sutton and Williams here. And, I think that might be a mistake. I just don't really understand their earlier contributions, given how much was done before. I just don't know. This whole notion of a score function goes way back. I mean, that's, at least the 70s. That's about to pop up. So I think there was incredibly inspirational work, but I just don't know what the scientific contributions were. So I got stuck. I had no one to help me. So I gave up. I wish I could fix it, you know. All right. So just again, we know that Q-learning solves this, what's called a Galerkin relaxation. And you get, for TD-learning, you have the same, basically with this formula for temporal difference, just by changing the definition of this underbar, you get the same sort of root finding problem. And TD1 solves this minimum norm problem. And I remember when I first saw this, I thought, that's gold. I'm always going to use TD1. It just didn't occur to me that who cares? You know, so what? If I solve this minimum norm problem, what does it imply about anything? So in terms of directly using these methods, I can't tell you, all right? But it turns out that for TD1, the fact that you've solved that minimum norm problem means that you've got this orthogonality principle, and that leads to magic. So the most compelling motivation for this stuff, the TD-learning, is for doing stochastic gradient descent. Okay, so I didn't get to cover this before, but at least in your exercises yesterday, I was proposing a randomized policy where with probability epsilon, you do something completely random, oblivious. And with probably 1 minus epsilon, you do something which is a smooth approximation to this Q-greedy policy. And it turns out that stabilizes Q-learning. So if you apply Q-learning with a linear function class, and you take epsilon small enough, and there's a formula in my paper, you can get stability of Q-learning. But it seems so circuitous. Design a Q function, do all this to get a policy. You know, why not just start with a collection of policies and find the best one in the class? You know? And for me, it's very strange because there's such crisp, perfect theory for that approach, but it never works for me. So I'm presenting something where there's elegant, perfect mathematics. I get stochastic gradient descent without bias. Perfect, motivated, awesome. When I run it, it doesn't work. It just blows up. And so people do hacks and hacks and hacks and hacks and hacks. Nobody does that. Nobody uses TD1. They use TD0. They use TD0 where there's no theory whatsoever. And they don't use, they just ignore everything. And I guess that doesn't work either. And that's why you have this clipping and all these things. When you do the clipping, is it gradient descent anymore? And if you're not using lambda equals 1, what on the earth are you doing? What are you estimating? It's so funny. So I even though this is the most beautiful theory, it needs a lot of work to really, you know, you need some good computer engineers and maybe some new science as well. All right, so I'm giving you beautiful math, and you know, you all have homework to make this more efficient in practice. Yeah, so forget this. So I'm going to look at the average cost criterion because I feel it's simpler to describe. I actually, last night, I wrote up a summary of Deb's talk to explain how it connects up with what I'm doing here. Okay? We might have time, actually. It's 10 to 10. All right, so I'm looking at I have an objective function, which is the long run average cost. That mu is the initial distribution for xn mu n. It doesn't matter because we can assume everything's ergodic. We can assume that for every theta, that induces a Markov chain, which is unit chain. That's what I really need. That's all I need. Yeah, so that's my objective function. I use that gamma because L was used for Lipschitz constants in my book. So it's an upside down L. And that's it. So we'd like to minimize this overall theta, and we'll use stochastic gradient descent. All right. Now, so I'm using this notation for the invariant probability mass function for this state action Markov chain. And that's my objective function I'd like to minimize. And now I'm introducing Q sub theta, because theta means something different. It's not the theta over there. For each theta, I've got a policy. You know, it's awful, isn't it? Notation is painful. This is called Poisson's equation, and it comes up in every aspect of life. And if you haven't seen it before, you haven't lived. Everywhere I go, it pops up. Ever since I was a grad student, it's the weirdest thing. Yeah, but anyway, really strange places it comes up. And so I've got something like a dynamic programming equation without the gamma. So if you look at the average cost or the discounted cost Bellman equation, there was a gamma over there, and there was no constant here. So it's exactly like a limiting case of the discounted cost Bellman equation. So what Schweitzer did is he took this equation and he differentiated both sides with respect to gamma. With respect to theta, because I'd like to get the gradient of this objective function because I want to perform gradient descent. And so when you take the gradient of both sides, you can go through and fool around. You have to use the fact that this expectation depends on the policy, as we'll see. So this is a way of writing it down. So this is a notation that I was using yesterday. T theta is a transition matrix for the joint process, okay? And I really should write that down. Okay, so for the joint process, X and U, I start off in X and U, and with this probability, I go to an X prime. And then when the new state appears, I choose the next input, as a randomized function of X prime. All right, it's this product form is really awesome, as we will see. Okay, so yeah. So what Schweitzer showed was this formula here, that the gradient of over here is just what's called the score function, the gradient, the log of this transition matrix, times the Q function. And I will prove this to you, I think. Do I prove it to you? No. It's so short, I'll just prove it to you. I'd say I didn't put it down here because doing math in PowerPoint is a mistake. But look how trivial you can imagine it is. I mean, I just take that thing and I interpret the gradient. Let's do it. I don't need this stuff anymore. Well, yes, I need that. That I need, but I can erase this stuff. Take 2 minutes. Well, it takes 2 minutes if you allow me to cheat with notation, but you will all agree that that looks like matrix vector multiplication, right? See the summation of a z prime, tz, z prime, blah, blah, blah. I don't want to have to write all that stuff down. Just I'll accept matrix vector multiplication just for a second, so I can save chalk. So I go through and I take the gradient with respect to theta, and I have to use the product rule. Okay, C is just a function of X and U, take its gradient, I get 0, right? Now, what do you think I'm going to do? I've got this grad Q theta, that looks ugly as hell, but it's also, there's a grad Q theta there. If I now average over the invariant distribution, using the fact that I've got this pi theta p theta equals pi theta, the invariance equation, you can think of this as a row vector times t theta is the same thing. So I hit both sides by that row vector, and these guys get canceled out. And so I end up with this weird thing here. And now I have to expand it out. I've got the summation over z of pi theta of z grad t theta from z to z prime, q of z prime, all right, and you'll notice again, this disappears because I cancel them out. When I average them out, the mean of this in steady state is the mean of that in steady state. Now, why did I leave some weird space here? Is because I didn't leave enough. To get that formula, you got to divide by t theta and multiply by t theta. And do you all see it here? Anybody remember the derivative of the log? So this ratio is the gradient of the log of t theta. That's the score function. And pi theta z, t theta z to z prime is a steady state distribution of the pair process, phi k plus 1. That's what that is. Is a oh, yes, but there's something missing here, right? You know, if you look at this, if I take for any z and z prime, if I take the log, I get a sum of terms, and one doesn't depend on theta. You know, that's fucking awesome. So that's the model that would really get you into trouble. You know, so Schweitzer didn't have a specific form, so he wasn't able to take advantage of the fact that the model disappears, and the gradient only depends on. You know, the gradient only depends on this tail part, which is model free. So it's just poetry, absolute poetry. Over and over and over again, you see the value of going from the process xk to the joint process xk uk. You know, if I just gave you a family of transition matrices p theta x to x prime, you get beautiful theory, but it would be model based. You know, you wouldn't be able to. You know, you'd use Schweitzer's sensitivity formula to gradient descent and all that, but you would need to know the family of p theta. Here you only need to know the policies which you designed. You don't need to know this transition matrix. You know, I do, because I do simulations to train my RL algorithms. So I need a model, but it's pretty cool that you don't need it. All right, so that's it. That's the formula. Now, you know, I think you might know where I'm going. Yeah. Where? Oh, no. It's because, well, here there's a missing sum over z prime. Yes. I mean, I skipped a step because I was saying that this thing here, this pi theta, that's a variation on pi of z, t theta z to z prime is the steady state for the bivariate process, phi k plus 1. But really, I shouldn't say that. Nothing here depends on z. So basically, I can sum over z first and use invariance, and all the z dependency falls away. You know, so thank you for asking about that. So yeah, that's equal to just a sum over z prime. And then I've got my q theta. And that's my score function, which I'm calling lambda. All right. And so, I've got a root finding problem. My goal is f bar of theta star equals 0, and I can go through and then use stochastic gradient descent to do that. And, so I need TD-learning to estimate Q theta. The score function is just sitting there waiting for me to play with. And there you go, done, actor-critic methods. And so what people do in practice is they come up with some big neural network and they estimate that, and then they do all the clipping and blah, 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 blah to fix it. But we've got that formula. Again, the thetas, the thetas, they mean something different there than there. But I don't need to know Q theta. I only need to know the expectation of this score function times this, fixed policy Q function. All right. And so all I care about is this projection on the span of the score function. Think of that as a basis. So I think, is that the next slide, hopefully? Well, yeah, first here's a really good example. I mean, so this is a really important, so in case of a Gibbs policy, or log linear, as Deb was calling, is it behind? Yes. So I've got I'm using size 0 for a really good reason, you'll see in a moment. So I've got an exponential of some linear function of theta, and there's a normalizing constant. This is just so this is a probability mass function. When I take its gradient, I take the log and then the gradient. When I take the log, of course, I'm going to get something linear, so that's why I'll get this term here. When I take the log of this and take the gradient, what I end up with is this function of x, which depends on theta as well, and it turns out to be a conditional expectation. So it's a conditional expectation of the basis function for the policy, using my policy there. So conditional expectation given x, right? And that's something useful. That structure turns out to be valuable, as we'll see. Okay, so again, this is a thing we'd like to do. And I might stick to Gibbs policies because it's so elegant, but that's that. All right, so I need this expectation to be 0, and what am I going to do? I think it's right here. Yeah, so going right back to here. So, basically I'm repeating what I had over here, and I need some new notation. What I'm going to do is, given the projection properties I talked about, I don't want to estimate Q theta. It's a waste of time. I want to estimate its projection onto the basis span by the score function. And so I just solved this. This is just TD1, but choosing, in the case of Gibbs, choosing the, always is choosing the gradient of the score function as my basis. That's it. Because of this orthogonality property. Yeah. Yeah, so that's it. So here's the algorithm then. It's just a notation I know is confusing. Again, I have a Q theta k, and I'm choosing this psi k just to be the gradient of the score function. Okay, these thetas are awful, but anyway. And since this is 0, why estimate this? Just estimate its projection onto the span of that score function. That's the message. Okay, and that's why you have this notation here. I want to find the closest function to Q theta in this pi norm. And so I've got to estimate that vector using TD1. And that's the algorithm. So I can, it turns out that the, where's my score? I guess I didn't realize, I'm skipping to Gibbs. I guess I didn't even realize I'm doing that. I'm just sticking with Gibbs policies. I forgot I had done that. It helps the notation. So the Q hat n theta phi k times the score function phi k, the mean of that is my gradient. So I've got a minus sign here because I'm doing gradient descent. I don't have a reward, I have a cost. And there's a matrix gain that people typically shove in here, which the natural gradient, stochastic gradient, the natural actor-critic algorithm has a particular form. And then for this, I just use the TD1 update. And I write this in this mysterious way because I don't want to have to explain to you TD1 for average cost. You'll have to see the book. But again, nobody ever does that. They stick in TD lambda, and because they see the variance is so big, so they just go for some bias. And the GN could be any positive definite matrix, but there's this one choice that everyone agrees is good. And that is this. Oh yeah, I mean, I should say, again, it's a 2 time scale algorithm, because again, we want to track. We want this Q hat n to approximate the fixed policy Q function for the current theta n. So you've got to crank up the gain on your estimates for this omega n to solve that projection problem. You've got high gain here. The ratio of this beta n and alpha n will go to infinity. And this works. It's stochastic gradient descent. As long as the ODE is stable, this will track the ODE, and everything's solved if you're a mathematician. If you're an engineer, yeah. But this is a thing you'll find. This is out of the book. You've got this approximate gradient, which I wrote down here generally, using different notation here for reasons explained in the book. I've got my score function. There's a temporal difference term here. And you'll notice here that Z dot, so you have to see the book. This is uses regeneration. So basically, it uses the fact that for this average cost Q function, you can represent it as a random sum up to regeneration time. You just pick any state action pair that you visit fairly often and do that. And that ends up modifying the eligibility vector update. Now lambda would be equal to 1 in TD1, but again, nobody does that. They take lambda equals 0 sometimes, even though, if you look at the equations, they don't mean anything if lambda is 0. And then here's the favorite choice for the matrix gain. You take it to the inverse of your estimate of this autocorrelation matrix, and that's what's known as natural actor-critic method. And it is natural when you're looking at parameter identification. It turns out to be the right thing to do. In this setting, I don't know if it's the best matrix gain. It's just what's popular today. We might come up with something better later on. Why no zap? Why am I saying no zap? No zap, right? Anybody know why? What's my goal here? What is this approximating? Anybody remember what we're trying to do? Remember, there's our goal. We're trying to find the best theta, which minimizes average cost. And what's that supposed to approximate it? Anybody? 1, 2, 3. Yeah, I mean, we're trying to optimize the policy by what means? Stochastic and gradient descent. This is supposed to approximate gradient descent. If I just shove in a matrix gain from ZAP, I don't know it's positive definite. And so what I end up doing is going to a local maximum instead of a local minimum. So no ZAP, no ZAP. It's not, if you had a problem with just quasi-convex or something, if you had some structure like that, if you knew a priori, then by all means go with ZAP. If you know there's a unique stationary point, then zap would be great, you know. But that's, we don't have conditions for that. In the tabular case, we do. I mean, if we're approximating all policies, then you can actually show there's some nice properties where you'd be justified. And another thing missing here is you really should add a regularizer, because like I said, if you've got a really good class of policies, the best policy might be with theta and going to infinity. And so you just want to try to make things compact. Right? And so there it is. And yeah, I think, oh yeah, and that's the thing, that's another thing that comes up, is that there's this thing that I talked about the advantage function for Q learning before. For TD learning, it's way more clear and intuitive. In the book, the notation I use is V. Just forgetting the thetas here. So I use V because A was taken. So the advantage function is the Q function minus this thing here, that's the fixed policy value function, you know. So you're taking that minus this. So this thing here, as gamma goes to 1, remains bounded. I mean, here, well, anyway. But it pops out naturally here. And so there's a big thing made about the fact that, you know, by here, oh Jesus, oh right here. So the conditional expectation of the score function given x is 0. It's an easy proof, I'm not going to give it. But there was a big deal made about 10 years ago, is that, wow, if that's the case, I can go through and replace this gradient thing. I can subtract any function of x, n, and get an unbiased estimator, another one. And then I forgot who it was, said, wow, let's subtract off the conditional mean, you know, but it was already done. It's already there. The conditional mean's already been subtracted. If you follow Condit's thesis, you're doing it already. You don't have to be told to do it. The problem is that nobody follows Condit's thesis. They try to approximate the entire Q function, and they have big variance. They say, oh, Jesus, let's not do that. Let's approximate the advantage function itself, because any function of x doesn't affect bias. But as we saw, it's automatic if you follow Condit's thesis. You're choosing a basis which estimates the advantage function, not the Q function. You know? And it's not, again, it's not an estimate. I mean, imagine if theta is one-dimensional. It's a one-dimensional parameter. You're trying to approximate the Q function, something which is maybe convex in X or whatever, there's some exotic thing, by, you know, by just a scalar times that gradient. They'll look nothing alike. Yet it's an unbiased estimator. It's really wild. I'm not criticizing anyone. I'm just saying the mismatch between theory and practice is so vast, it's mind-blowing. You know? All right, I think that's it. And so if anybody wants to, I could go through and make the connection with Deb. But I don't know if we want to or not. I mean, you want to? Yeah. I think it's worthwhile. So Deb was looking at the discounted cost criterion, and basically, I just want to go through step by step what he said. I think it's worth going back and comparing. Okay. If I take any function of the first n state action pairs, you know, I've got some initial, so not in steady state. So mu0 is just some initial distribution. You know, I've got this product which defines the probability distribution on strings. Okay. And so what I'd like to do is take the gradient of that and get a formula for it. And the score function is going to pop out again. Because, T theta is this product, and, and it looks really horrible. You think about taking a derivative of this product, it looks awful, but then this logarithm saved the day. So let's just do that. So like I said, the gradient of this thing I'd like to take the gradient of divided by itself is a gradient of the log, right? And when I take a log of a product, I get the sum of the logs. Yay. All right, so now I can take the gradient of this, and I'll get a sum of the score function. All right, just do it in your head. I've got a log of a product, that's the sum of the logs. And when I take the gradient of the log of this, that was my score function. Yeah, that's it. So that was that's what that is. That's the score functions. And you notice that this depends on zi minus 1 zi, but the score function only depends on the second term. So that's why I get a sum from 1 to n of just zi's. There's no zi minus 1. And then, I can take this to the other side, because what I really care about is the gradient of this. So take this gradient is the sum of the score functions times this product. And so when I take the gradient of this, I'm going to just take the gradient inside, and I know this gradient is the sum of the score functions times the same thing that appeared before. So that is the thing, that's the Parby distribution on strings. And therefore, you can just reinterpret it. The gradient of G is just, I have an expectation, this is before, but I've got to stick in the sum of the score functions. Just algebra, I had expectations are just obtained like this, and I get this. All right. And so it's a weird thing. It's like this is like sort of like a likelihood ratio. It's a non-signed likelihood ratio, which encodes the gradient. It's quite cool. All right. All right. So so now let's just go back and take G just to be the cost. Okay. So basically, I'd like to minimize. So now I'm looking at the discounted cost problem. I've given some initial distribution. I'd like to minimize this over all theta. And I'll apply gradient descent. And so if I take the gradient with respect to theta, I don't need this notation. I'll just take the gradient of each term and use the formula I just showed you. Okay. So if I take the gradient of this, the gradient of that is a sum from 1 to n of the score functions times C of phi n. Because C of phi n is what I had this G before I just a general function. And what do you do now? I've got a double sum. Well, you always flip the order of summation because something magical happens. And then you get this beautiful formula. So what have I done here? I've taken the sum from I equals 1 to infinity outside. And then here I've got a sum from n equals I to infinity inside. And you notice I have a gamma to the n. Well, I wrote that as gamma to the n minus I times gamma to the I. And the reason for doing that is that that looks like a Q function. So that there, since I have an expectation, that turns out I could just replace that by the discounted cost Q function, evaluated at the starting point, phi I. Wow, that's it. Okay. So that's a sort of a derivation of what Deb was talking about on Tuesday. And so that's a big damn sum. And you could go through and do gradient descent with that. It sure gives you an idea of the variance issues. So once more, I don't care about estimating Q theta. I only estimate its projection onto the span of the score function elements. Okay, but it's just that gamma is going to be 0.99 or big, and so the random object here, even though it's a random variable finite mean, if you just try to use this for gradient descent, you get a crazy high variance algorithm. And so that's really an issue. And I can show you examples where I've got an estimate for a gradient, not here, but in the average cost case, I just fix theta and draw samples and make a histogram to see the variance of the gradient estimate. And I see it's 10 to the 5th, 10 to the 6th, just, absurd, absolutely absurd. And so it's worthless. And so you do clipping, but then if you clip it, is it unbiased? And is it, why does it work? Especially the tiny clipping that's proposed in the papers, these delta clippings. You take some random variable with variance 1,000,000, and I clip it, the plus or minus delta, its mean is what? Where's it going? It's really a, but to be fair, those algorithms with the clipping don't do the gradient descent anymore. They try to fix that by looking at constrained optimization problem. It's not just simple clipping. That would be nuts, but still, yeah, it's wild. Okay. Oh, here's an example. So this was from a change detection problem. All we did is it was scalar. For each theta, we just estimate the variance to repeated trials, just to do that. And we found that, 10 to the 4th near theta star went to 10 to the 5th. It would go down to, way out here to only 10. Is that the variance of the standard? Yeah, the variance. And we got, what's amazing is in this run, we actually got the right answer when we estimated the gradient. So we're not writing an algorithm. We're just, for each theta, we're estimating the gradient using Monte Carlo and getting a plot. But when you go through and integrate this numerically, you get a perfect, answer. So this, you get the answer just by using these formulas, right? But if you tried to use stochastic gradient descent, it would just blow up, because you get these variances like that, what are you going to do? It's just going to blow up, completely worthless. And unless you do some, clever hacking like you see in the literature. So far, I'm not impressed. And if you do analysis with lambda equals 0, and you use this minimal basis, it's a joke, And that's why people go the other route. They'll use some giant neural network to estimate the Q function or the advantage function with lambda equals 0, And it seems so sad. I bet there's a better way. Because I bet the variance is worse, because you estimate, you like if theta is one-dimensional, I've got a one-dimensional optimization problem, and for some reason I'm making it a billion-dimensional. I bet there's an orthogonality principle that shows that the variance is higher. I don't think it's helping. Now, making lambda equals 0, though, that's cool, but there's no theory. The whole beauty of actor-critic is that there's a theory that justifies it. If you make lambda equals 0, what the hell are you doing? It's just the theory becomes as weak as Q-learning. So it's incredible. But so, the two things that are interesting to me is I said like different theory or methods for actor-critic. When I say without the noise, without the massive variance, I suspect that we should just give up on this theory. That if you just use zero-order methods, I bet they're much more reliable than all this elegant theory. Even though I love this so much, it's one of my favorite topics in this area. My favorite topics in Markov chain theory. I just don't see any value yet. It's so sad. And if you just go and apply, these Kiefer-Wolfowitz, if you've seen this, or SPSA, empirically it works better for me, and it's easier you understand the bias much better, all of that. But maybe something else will come along. But that is it. I'm done. I welcome your questions. All trivial. Yes. Oh, yeah. Oh, this thing here. Yeah. It's so cool. Yeah, I'm going to rewrite these slides with omegas here, because the theta is meaning two different things in one talk. It's just I was lazy. But anyway, so I've got this objective, take the gradient, that's all clear. And then, so there's nothing here. All I did is I took the sum outside and all that. But right here, I have an expectation of psi times 0 times c of phi n. And there, so I did a shift right here. I'd say it's stationary, whether if I shift time, it doesn't change a thing. Okay, so I went from k to 0 here. And q theta k is by phi k, or q phi 0 is by definition the conditional expectation of that given phi 0. So I just got rid of the conditional expectation because I can, because there's an expectation outside. You know, the expectation of a conditional expectation is the expectation. And then here I just subtracted n. So I've subtracted n from n, I got 0. Subtract n from 0, I get minus n. So minus n, 0. You know, and then, so that's why I said that the summation from 0 to infinity of gamma to the n psi of minus n was by definition the eligibility vector times 0 with lambda equals 0. That was just the definition, you know. And then here again, I can say, well, I can shift time any way I want. You know, so 0 and whatever, put in your favorite number. You know. And I guess this is probably what Benvenure did, you know, back when he was a grad student. You know, he probably started with this rather than trying to interpret TD learning. You know, it's much easier just to start with this. And, you know. But just imagine the coincidence, you know, that he developed this theory exactly when Vijay Kanda was working with Borkar on gradient descent, and knew that this was important, you know. And so, you know, Benvenure gave this gift to Vijay Kumar, you know, who arrived just when Benvenure was finishing his PhD. Just remarkable.
That goal, we say in theta, then obviously you're not going to use absolute frequencies, but you're going to say pi theta minus pi, you know, the actual pi. Can this be extended in that method where we literally try to minimize the distance between the policies themselves rather than?
Oh no, but I mean, my only goal is to get stochastic gradient descent working. You know, it depends on your goals. I mean, here my goal is to write down a simple stochastic gradient descent algorithm and argue that I don't have to estimate this guy. You know, so my goal, there's only one way to do it, is I want to show that, use the fact that this is 0. Yeah, when you solve this projection problem, you get this orthogonality property. So that it's just my goal is the fact that I want to throw Q away and replace it by this approximation, you know. So yeah, so what would your goal be?
Yeah. So in this case, my goal would be rather than make rather than make sure that my Q value is matched, which is basically what that difference is. I'm more interested in making sure that my policies match.
Oh, well, no, but I mean, I like what I'd love is my policy to approximate the optimal policy. And good luck on theory for that. You know, that would, I mean, if there was an equation for that, that would be awesome, you know. But that's the thing, is that that's the issue, is we've got all these pretty equations in value function space and no pretty equations in policy space, you know. You know, it's yeah, so I wouldn't know. Yeah, I wouldn't know how to do that. If I looked at some distance between Q, you know, phi theta and phi theta star, I wouldn't know how to even start to analyze that, you know. Yeah, because, you know, what happens over and over again is you have something you don't know, you know, and just because of all the formulas, you translate that into something that you can observe. The cost times an eligibility vector. With the policies, if you did something like that, you'd still have phi star sitting in your face you couldn't get rid of, you know. So if you could come up with something where you have a gradient formula where you try and minimize the distance between, in some sort of distance between that theta policy and the optimal, and you could get a formula for the gradient, and you know, the optimal policy would be there. If you could somehow get rid of it by transformations like this, you know, you'd get the next Turing prize. You know, that would be an incredible breakthrough. And I'm not saying it's impossible. You would need the right metric. You'd have to define a really clever distance between policies. And so far, the only distance we have is, well, you know, I mean, just, is the cost big or not? That's, you know. Yeah,
Slide, and I think think maybe slide 17 or something. You had the inverse of your transition. For
17.
Oh yeah, there.
Oh, yeah, yeah.
Oh yeah, so
Yeah, this idea.
stuff like
Oh, no, no, no. No, I'm just saying that's a fact. You know, the gradient of the log, I'm just using the chain rule.
true, but we know that the inverse.
Oh, no, these are scalars. Oh, no, 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 these are all scalars. Yeah, yeah, yeah. Oh, absolutely. If we were to try to inverse the matrices, we'd be dead. I'm just saying I've got a sum there over just this massive number of Z's. But inside, it's all scalar. And so if I take the gradient of that expectation, I can take the gradient within the sum, and then I'm just taking the gradient of a scalar. Yeah, you know, we'd be dead if it was matrices. Yeah. So this is for every sequence of Z's. I've got this formula, and then everything falls apart nicely. Yeah. Yeah, thanks. Yeah, the next slide is just definitions, because the gradient of the log of t, yeah. Yeah. And there's, oh, 19, okay. Well, it's still 18, but is it here or? Okay.
So we take in the first step, take the gradient with the object.
Yeah.
And there's an assumption, right? But we think that C is not differentiable because
Oh, no, no, that's what's so amazing. Well, the C is not a function of theta, so.
as we change that.
No, but C is a function, it's not. So if you go back to my original equation, here I just have any function G. I've got the representation of the expectation. And then with some work, I get the gradient. You see, the T theta is, the theta dependency is here. G doesn't depend on theta. So that's when I'm able to take the gradient of both sides of this equation. I don't have to think about G. Any function. I'm just saying, I wanted to keep general, just as Deb did last on Tuesday. I'm just saying for any function G, because you might have another objective. If you're looking at like risk-sensitive cost, you end up with G's that depend on, you know, something like this. But yeah, you really have to step, you have to look at really into the trees. What you're saying is absolutely correct, that this random variable depends on theta, you know. But when you express it like this, you can separate G or C, which doesn't depend on theta, with what really does. So yeah, so this formula is universal. You know, okay. But you get something which is pretty useless. Yeah, I mean, just imagine gamma close to 1. Just, yeah, I would change my, yeah, I mean, that's why people don't even use people. That's why you see so many papers where they're just looking at finite horizon optimal control, you know. So instead of summing to infinity, just sum down and take m equals 1, you know. And you know, if the time horizon isn't big, you can get a really crappy policy. I mean, it's really, it can be very myopic. You know, and optimal control, I mean, people control, again, gamma equals 0.99 is small, because it corresponds to a time horizon of about 100. In a lot of examples, that's really small. It depends on the time steps and all that. So, you know, so the variance issue is just inherent. You know. Okay, so I guess time for cookies. Thank you.